Welcome to our video on vector projections. I'm Asha.
And I'm Andrew.
And today we're going to talk about vector projections. So the definition of a vector projection is it's like a shadow onto another vector, and there's a formula to figure out like the projection of one vector onto the other. So the formula is the projection of like A onto vector B would be the dot product of vector A times B over the magnitude of vector B squared, and then multiplied by vector B. So using this formula, you can find the projection of one vector onto another. So we're going to do a couple of examples. So this is a drawing of what a vector projection would be. So basically we're given one vector, which is right here. And like, let's say that this is like vector A. And right here we're given another vector. And this entire vector right here would be vector B. And so basically what you're trying to find is like from here to here is the projection of vector A onto vector B. So you're trying to find the length in between, this length right here, where the question mark is. And that is the vector projection of A onto B. So we're going to do a couple of examples. So in this problem, we're going to find the vector projection of vector V onto vector W. So we have our equation set up here. Is the dot product of vector V and vector W over the magnitude of vector W squared times vector W. So the dot product of vector V and vector W is 0. And the magnitude squared of vector W is 10. And then you multiply that by vector W. And since it's 0, what happens is it cancels out. So you're going to end up with 0, 0. And that is the vector projection of vector V onto vector W.
This is the vector projection already laid out. As you can see, it's a dot product of vector S times vector T over the magnitude squared times vector T. And once you simplify it all out, it should equal negative 17 over 13 times vector T. And once you multiply those two together, you should get the vector projection of 3.9 and 2.6. Okay, so for our last problem, we're going to do a real-life application for vector projections. So the problem is we have a 300-pound car that is parked on a hill with an incline of 16 degrees. How much force is needed to keep the car on the hill? So first, you're going to have to draw a free body diagram because that'll help you solve this problem, giving you visual aid. So you have an incline of 16 degrees. And you have your wonderful, tiny 300-pound car on this incline, on this hill. So you're going to have to draw out all of the forces that are enacting on the car. So you have the force of gravity times the mass, in which that's just 300 pounds. Like so. And then you also have the force of the road pushing on the car, which for physics students knows that this is called the force, the natural force, or F of n. So what you're going to have to try to find is how much force is needed to keep the car on the hill. So to find that, it's just the shadow of F of n on the road, which is this force. So to find this force, you're going to use SOHCAHTOA, because through Newton's third law, F of n is equal to this vector. So you don't know the vector, this vector. Through SOHCAHTOA, you could find that it is just 300 times sine of theta. And if you didn't know, this is also theta. And then once you multiply those out, since f of n is equal to this vector, you can find how much force is needed to keep the car on the hill, or how much force the car is pushing on the road. If you multiply those out, you'll get 82.6 pounds of vertical force on the road. And that's your answer.
Thank you for watching our video, and we hope you learned something about vector projections.